Hi everyone, so today we will do this question 935. It's called the night dialer and it's one of the frequently asked questions by Bloomberg, and I'm interviewing with them, so I just wanted to do this. Okay, so we'll begin with reading the problem and then I will come up with solution A and then we'll try to improve it. Okay, so let's get started. So the question says, the chess knight has a unique movement. It may move 2 squares vertically and 1 square horizontally, so like this, or 2 squares horizontally and 1 vertically, with both forming the shape of an L. The possible movements of chess knight are shown in the diagram. So I think we are all aware of how the chess knight works. It makes a movement like a L. So 2 steps up, 1 step right, 2 step left, 1 step up, or 2 steps left, 1 step down. Okay. Now we have a chess knight and a phone pad. As shown below, the knight can only stand a minute on the numeric cell, which is the blue cell. Given an integer, return how many distinct phone numbers length n we can dial. You are allowed to place the knight on any numeric cell initially, and then you should perform n-1 jumps to dial a number of length n. All jumps should be valid knight jumps. As the answer may be very large, return the answer modulo 10 to the power 9 plus 7. Okay, so when I think about this question, I think like, how would I do this, right? So let's first draw the keypad. So here I am drawing the keypad just for visualization purpose. And okay, so if I was kind of solving this by myself and I was not even doing it algorithmically, right? How would I do that? So I would start at supposedly, let's say 1, and then I would go to what's possible next. I would say go right 1 2 step at 6, then from here go, let's say, back at 1, or let's say for our case 7 here, so on and so forth. So if n is 3, I could do 1 6 7, 1 6 1. So you see the pattern, right? So what does this kind of indicate, or what does this remind you? For me, it indicates recursion. Okay. Oh wow, change the pen. Okay, so this indicates recursion. Okay, so if you have done problems like the islands, number of islands, and any like DFS problems, you can think of like that's one way to solve it. Okay, so I am first going to solve this question thinking about it like an island problem, that oh, I can't go here and here, but I can go to all these places. Okay, so what would our grid look like? Our grid would be something that has 1 2 3 4 rows and 3 columns, right? We have that, and then we'll initialize these n1s. Let's say, so if this is row 0 1 2 3 0 1 2, so let's say 3 0 and 3 2 would be something, let's say 0, or something that signifies that you can't get there. Okay, once we have that grid, you can visualize this as a grid problem where you use DFS, right? So how do we go about a DFS problem, and especially this problem? Okay, so let's start by thinking about it. So first is, you want to first make the grid. Okay, so let's make the grid. I'm switching off onto the Leetcode so we can write as we go. Okay, so I've come here and from what I showed in the picture, I'll just make a grid. Okay, so a grid, I'm using Python, will be I in range 3, 0, 1, 2, 3, 0, 1, 2, that is number of columns, and then number of rows. Okay, now I want to make those specific last two, like these red ones, as something that means I cannot go there. So let's say if I say 0 for something that we can go there, we can say 1 for something that we can't go there. So we'll do grid 3, 0 as, 3, 0 as say 1, and we'll do grid 3 and 2 as 1, and we'll have maybe a self.count, which is at 0, and count is the number of possible solutions. Okay, now like TFS, what do? We iterate through the loop. We iterate through a loop, and if we can go there, we just recurse, right, on a helper function. For j in range 2, 0, 2. Okay. No, I think 4 and 3. So row is number 4, and columns are 3. Okay. Now if I say if grid 3, not grid I, j, if this instance is not, if it is equal to 0, means we can go here, we call the helper function, and we will write the helper function, and then we return the self.count. Okay, this is the base. Now we have to write this helper function. So how do we imagine the helper function working? I'm just going to hide this. Okay, so how do we visualize the helper function is going to be working like, right? So let's try to kind of think about the helper function. So we have a helper function. It should take in obviously the index of the element we're looking at, and maybe the n value, or like how many numbers have we already gathered so far. Okay, and do we need anything else? Okay. Okay, let's start with that. So we have to first get rid of return on all the base cases where I is less than 0, or I is greater than 3, or j is less than 0, or j is greater than 2. Okay, and that's the base case, so we just return. Otherwise, if the current length is equal to what we're looking for, the n size, we do self.count plus 1. Okay, and we return. Okay, now for the other logic, we have to call this helper function again. Okay, and if we look here, one knight can take 1, 2, 3, 4, 5, 6, 7, 8 calls. So we'll have 8 calls to the helper. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now let's imagine the knight here, and we're looking at these 2 arrows, so it will be 2 rows back and 1 row left, 1 row negative, and 1 column negative and 1 column positive. So we do 2 rows back, 1 column negative, and 1 column positive. Okay, then we look supposedly here, we look here, 2 columns back, 1 row up, 1 row down. So 2 columns back, okay, 1 row plus, 1 row minus. Okay, now we look here, 2 rows front, 1 column back, 1 column front. Okay, So 2 rows front, 1 column back, and 1 column front. Similarly, 2 columns front, 1 row plus and 1 row minus. Okay, and are we missing something else? Yes, we are. So we cannot go on certain blocks, right? The specifically the hash and the star. So we want to not go there. Okay, so we'll say current length is 1 because this is the first index. Okay, so we want to also say or grid I j equals to 1. Okay, so now, and the question says that we should also return the modulo. So I think the modulo is this, and we can do 8, 1, 2, 3, 4, 5, 6, 7, 8, and 7. And just in case, this is like the basic thing, so I just want to run these small test cases to show you that it works. Oh, what did I do? Maximum. Okay, did I miss something? Equals to 1, then I return, and 4, 3. Okay, maximum depth returned. Okay, let me recheck. So I come here, I make a so it looks like that I have forgotten to increase the length at every recursion step. So I'm going to update all these helper function calls with their new length. And retry, and yeah, so this works. Okay, so now let's think about how can we kind of do it without recursion. Okay, so if we look at the board, we can see some patterns. Okay, let's start. So if you are at 1, right, how could you have gotten at 1? Okay, it could have been through an L shape, either like this or like this. Okay, so you could have gotten to 1 from 6 or 7. Okay, similarly, if you were looking at say 6, how can you have gotten here? You change the color, be like this, or this. So to get to 6, you might have gotten through 1 or 0 or 7. Okay, so at each instance we can get through like just a limited number of before ones. Okay, so I'll write out for first one, for let's say 0. For 0, let me clear this again so we can have a fresh diagram to work with. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So to come to 0, I would have come from where? Would have come from here or here. So I would have come from either 4 or 6. Then for 1 we did it, that would be 6, 6 or 8. Sorry, this will be 8. 6 or 8. Okay, and similarly for 2 we would have come from 7, 9. Okay, so on and so forth. Okay, now if we have, like, we think of a dynamic programming table. Okay, so if we say that the columns represent the numbers 0, so the columns represent the value 0 to 9, and the rows represent the number of steps we need to take. So if n is 3, so that will be 1, 2, 3. Okay, but let's assume it starts from 0, so we do first row will be 0. For the first count it will be 1, because we can start from any position, so we can always have gotten to any position in the first row by 1 step. For the second one, how would we think about this? It would be all the positions in the previous row that would meet our moves. Like we have decided for 0, we could have come from 4 or 6, right? So in the previous row, whatever the count was for 4 or 6, we add those things together. Okay, so if you can see, for the 0th thing, I look at the what's in the previous row, and I look for the fourth value and the 6th value, and similarly for the first one we look at the 6th and the 8th. So I hope you can see the pattern, and I will quickly code it up for you in a few.